Alright, so this is going to be the first of a series of videos for the last couple weeks of our 8-week course. We've just got done learning how to solve higher order linear differential equations, and we're going to focus on one application which really illustrates how this applies to things in reality, and this is going to be what's called harmonic motion. And then we're going to focus on also a new method for solving problems. So we'll have a new third method involving something called the Laplace transform. So in this first video, I just want to explain basically what the kinds of problems we'll be looking at and the idea behind this method, but it'll take some time to actually understand the aspects of the method. So this first video, we're not going to actually solve anything. We're just going to explain some qualitative information about it. So harmonic motion models lots of a variety of situations in physics and engineering, and it boils down to a simplified model, which you see here, which is basically the idea of you have some object with some mass hanging from a spring, and that object may be forced or caused to move, bounce up and down on the spring, and based on some initial observations, information about how big the mass is, what kind of spring is being used, how to compensate for air resistance and other external forces which may be acting on the object, we will create a model which is going to be a second order linear differential equation or initial value problem, which when solved will actually allow us to predict the solution, which is going to be x of t, which describes the motion of this object as it goes up and down over time. So you can see what we're going to basically be considering is x. When x is 0, that's when the mass is sitting still at rest, kind of the natural position of the spring. If you hang a mass from the spring, it'll come to rest. That is the height 0. So when the mass is below that line, its x of t is going to be negative, and when it's above, it's going to be positive. So in the notes I posted, I go through basic harmonic motion and go through examples of how this is the actual model that we have once we kind of organize it into a second order initial value problem. And we have all these parameters involved, m, a, and k. And there's some given function f of t, and we know that the initial position is some number x sub 0, and the initial velocity is some number v sub 0. So basic idea is we have all this, once we have all that information, we can predict the future locations of the object over time. So we just need to know what all these things stand for. So m is the mass of the object. All right, so keep in mind, mass is not weight. Weight is a force. Mass is just a scalar constant. All right, you have the same mass whether you're on Earth or on the moon, but your weight is different because the pull of gravity is different on those two locations. So keep in mind, you may be given a weight of the object. You're going to have to convert that into the mass to plug it into this formula. So you have to be careful with the units, whether you're using English units with pounds and what are called slugs, and then or the metric system where you're using maybe grams, kilograms, and force of newtons. So just be aware of those. Again, if you don't know how to convert those, just do a Google search how to convert this to that, and there's calculators that'll help you. So as in the notes, and as I explained, this coefficient a, which is on the x prime term, remember x prime is really the velocity function, that's the coefficient of air resistance. We saw that earlier when we talked about problems involving air resistance. Air resistance works in the opposite direction the object is traveling to slow it down. So in our model, we assume this number is positive, and then in our model above we see that the model is as it is because we've assumed a is a positive value. K is going to be what's called the spring constant. So every spring is different. There are stronger springs and weaker springs, ones that are easier or less easy to stretch or compress. So there's some constant depending on the spring that we're actually using. And again, these situations apply to other situations where there isn't a spring. There's something oscillating in kind of not even being connected to something. Some particle of physics could be oscillating or something caused by some electromagnetic field. That electromagnetic field is acting like a spring, and therefore there is some kind of constant that is connected to that, and depending on the kind of particles you're talking about. So this very simplified model actually does apply to many, many things. And again, this number x subscript 0 is just the initial position that we observe in the object, and v sub 0 is the initial velocity. And again, velocity, I'm gonna focus on velocity being positive, meaning it's moving up, negative moving down. Again, this is something that everybody has to choose how they want to do it. You just have to adjust your work to make it consistent so that the answer in the end has the same practical meaning. And then finally, other than air resistance and the spring constant, there could be some external force acting on the object, forcing it to move. So you could think of one possible thing is that where the spring is attached, that might be moving up and down too, to try to make the mass work or move up and down. You can think of the kind of child's toy with a little paddle ball. There's a ball on a rubber band, and you have to shake it to make the ball bounce back and forth. That's somewhat a sort of an example of harmonic motion. It's not exactly the same because you're actually hitting the ball with an impact force, but we will talk about how you can deal with impact forces a little bit later. So this is the model, and the motivation behind this method is because of what I just said about impact forces. We'll see later that when an object is moving and it's struck by something, that force is really just an instantaneous force. It's applied over no time interval, really. I mean, it may be a really, really small time interval, but for our measurement tools, that's essentially instantaneous because the precision of our tools may not be able to measure that small amount of time. So we think of it as instantaneous. So in order to deal with such things, we're going to have to come up with another method because impact or impulse forces are actually given by things that are not functions. They're actually what mathematicians call distributions. But these things are sort of like functions, and sometimes there are functions related to them that we can use to solve problems. So since these things are not necessarily functions, the methods we've talked about, undetermined coefficients and variation of parameters, may not work. So again, I'm just saying, imagine that we have an object in harmonic motion and it's just struck by something. So we want to be careful when we're dealing with impulsive or impact forces that the method we use is going to have to be a different method than the ones we talked about. And then that's what we're talking about, the Laplace transform, and we'll get into that. So that's our another method is needed, and that's going to be the Laplace transform. So the Laplace transform is a linear operator. It takes a function, calculates a new function from it. Okay. So again, if f is some function we know of, say, time, we plug it into this operation L at s. So we have to plug in a function and the number. This s is now the input of the new function LF. And notice what we're basically doing. We're integrating from 0 to infinity our function, but our function times an exponential, which has our integration variable t, but it also has this fixed number s. And so as we vary s, this integral has a different value. So this creates a function in s. So the idea is we start with an equation, and we just plug both sides of the equation into this Laplace transform. And by linearity, we can split the terms and factor out constants, and we have this new equation, which is equivalent. So what we've done is we've transformed our problem into a new problem. And this new problem involves identifying a new function we're going to call capital X, which is the Laplace transform of our solution. So if we can identify that function from this new equation, then all we have to do is invert the Laplace transform. So what we're going to see is every function has a Laplace transform, and it's unique. And this goes back the other way. If a function is a Laplace transform, the function it is the Laplace transform of is unique. So it's an invertible operation. So we're transforming the problem, solving the new problem, and then inverting our transformation to get back to the function which we want, which is lowercase x. So again, here's our formula for Laplace transform of a function f. Again, this notation L of f is just a label of a function, just like f is a label of a function. The input of f is I'm going to focus on t for time because we're doing physics problems, and LF we have to use some other letter, so we're going to use s. In your book, notice you're going to see problems where they use all kinds of different letters. The point is there's one letter for the function, and there's a different letter used for when you use the Laplace transform. Doesn't matter what those letters are. So again, this whole tool was developed because of these idea of impulsive forces and problems in physics that these other methods couldn't deal with. Again, notational thing. When we're talking about labels and functions like that, we're just going to, instead of writing this complicated L of f of s, we're going to, if I have a function called f, I'm going to just refer to its Laplace transform as capital F of s. So capital F of s is the Laplace transform of some function, lowercase f of t, and capital X of s would be the Laplace transform of some function of time, lowercase x of t. Just so we know when we see that uppercase letter, we know, oh, this is the Laplace transform of some function that I'm looking for. And then we will have to then invert the process to find the function that we're looking for. Again, don't get caught up in all the letters that are used. I'm going to just always use T and S. All right, your book's not. So if you want to do problems in the book and you want to just translate your initial variable input to t all the time and then always use s for the Laplace transform, you may save yourself some trouble in getting confused about how letters are used. So this is part of doing math. You have to be able to deal with formulas that use certain letters and then applying those formulas to a situation where some other letters are used. You just have to translate. So what must we learn? Once we've transformed our problem, we need to know, how do you actually determine the Laplace transform of a function? Whatever this given f of t is, I need to figure out what its Laplace transform is. Luckily, this has been around for a long time, so basically a lot of the basic functions have been computed and stored in tables. And so we can just refer to tables, and your book has a huge table. But again, remember, it's using letters that may be not the letters we're using. I'm using T and S. T for the function, S for the input for the Laplace transform. So you have to translate the table when you use it. After we're going to basically identify some formulas that have been proven about the Laplace transform, and I will actually show you some of these proofs. They're not difficult, but understanding the proofs sometimes makes this less mysterious. So we look for formulas which allow for simplifications. And then once we do that, once we're going to solve this problem for this function Laplace transform of the function x we're looking for, we just have to invert that, apply the inverse Laplace transform to that, which means looking at a table and determining what this function x is that we are desiring. Again, keep in mind, remember what we said about linear operators, there's no standard notation. I use parentheses here. The context is this L is the Laplace transform, so whatever I'm inputting is a function. Okay, so the fact that there's parentheses here is the same as what we have over here with brackets. All right, your book will use the brackets, and I will try to use the brackets most of the time, but this is not a standard thing. Context determines what something means, not the specific notation. Like any language, math has lots of similar ways of writing the same thing. So you just have to be aware of those things and not get confused by that. All right, so that's the basic idea of what we're going to do. It's a basic three-step process. And for the second order problems that we're going to focus on, we can basically figure out a formula for our solution, which will basically mean that we'll plug in all our given information, which is the mass, this number A, this number K, our initial condition values. We'll plug all those into this formula, and what we're going to see is that our solution X is going to be the inverse Laplace transform of some function that we have, some function of S. And then we'll just have to figure out what that function X is, knowing that this function we know is the Laplace transform of it. So once that part is not easy, it's going to take some algebraic work and use of tables to identify, and use of a few formulas to identify things. But in the end, there won't be a lot of calculations you'll have to do. It'll be a lot of bookkeeping, using formulas, recopying things to look different but equivalent. And then occasionally you will have to compute some integrals. But most of the work is done by applying formulas and using a table for the Laplace transforms of basic functions that we're going to run into.